Have you ever just stopped and wondered, how in the world does your body defend itself against millions of different germs? I mean, invaders it has never ever seen before. How does it possibly create a unique, custom-made weapon for every single one of those threats? Well, the answer is one of the most elegant and frankly genius systems in all of nature, and we're about to dive deep into how it all works. To really get our heads around this, we're going to follow the same path that scientists did. We'll start with the huge problem they were trying to solve, look at the clever but ultimately flawed theories they first came up with, and then we'll get into the modern view that completely changed the game. We'll even check out some strange exceptions that actually help prove the rules. So first things first, let's really set the stage for the challenge here. This wasn't just some small puzzle. This was a massive biological paradox that had scientists scratching their heads for decades. This is the big one, right? It's not like your body has some pre-written instruction manual for every possible virus, bacteria, or fungus out there in the world. It has to improvise on the fly, and it has to do it with unbelievable precision and speed. So, how on earth is that even possible? You know, the first logical guess that scientists made kind of makes sense. The idea was that the invader itself must somehow provide the instructions for its own destruction. These early ideas were called instructive theories. The direct template theory was pretty intuitive. Picture a blacksmith forging a key by literally pressing hot metal against the lock it needs to open. The theory was that the antigen acted as that mold. A later version, the indirect theory, suggested the antigen somehow permanently changed the cell's genetics. Now, these were brilliant ideas for their time, but they had a huge, glaring flaw. They couldn't explain immunological memory. If the mold is gone, how does your body remember how to fight that same germ years later? And that one question, that one hole in the theory about memory, it forced scientists to realize they were thinking about the problem completely backwards. The answer wasn't about the body being instructed by an invader at all. It was about the body selecting a solution that was already there. And that leads us to the modern and now universally accepted view, the clonal selection theory. And the big idea here is so cool. Your body doesn't invent a new weapon on the spot. It picks the perfect one from a massive, pre-existing arsenal. This quote from the scientist Macfarlane Burnett, it just nails the entire shift in thinking. He realized the special lock and key fit, that unique weapon for each invader, wasn't created on demand. The secret was already programmed into the individual immune cell long before the invader ever showed up. So here's the bottom line. Your body creates millions of different immune cells, and each one wears a totally unique receptor on its surface. Think of it like a differently shaped keyhole. When a virus, the key, shows up, it doesn't teach the body how to make a keyhole. It just bounces around until by pure chance it finds the one cell out of millions that it fits into perfectly. And that perfect match, well, that's the signal to sound the alarms and build an army. Okay, so that's the big picture theory. But how does it actually play out on the ground? Well, it turns out it's a beautifully coordinated dance between three main types of immune cells. It all kicks off with a scout. A cell called an antigen-presenting cell, or an APC for short, is constantly patrolling your tissues. When it finds something foreign, like a bacterium, its first job is to just eat it. Now here's where things get really clever. The APC doesn't just destroy the invader and forget about it. No, it breaks it into pieces, takes one of those pieces and displays it on its outer surface using a special molecule called an MHC protein. This is basically the immune system's version of creating a wanted poster for everyone else to see. That wanted poster is now shown to another key player, the helper T cell. And this is where that incredible specificity comes in again. Only a T cell with a receptor that is a perfect 1 in a million match for that specific piece of the invader can bind to it. This is a critical security check to make sure the threat is real. Once the helper T-cell commander is activated and convinced of the threat, it goes searching for the final member of the team, the B cell. But not just any B cell. It's looking for the one specific B cell that has also already found and latched on to this exact same invader. When it finds it, the T-cell gives it the final green light using chemical messengers called cytokines. And this is the moment where the clonal selection theory really comes to life and gets its name. As soon as that B cell gets the activation signal, it starts dividing and dividing and dividing. This is called clonal proliferation. From that one single perfectly matched cell, the body starts building an entire army of identical soldiers. And finally, most of these newly cloned B cells transform into something called plasma cells.
And you can think of these as the ultimate weapons factories. They are antibody-making machines churning out thousands of antibodies per second, the very same antibodies that were coded for by that very first cell that made the perfect match.
All right, so we've got the process down. But what makes something foreign enough to even trigger this whole complicated cascade? Why does your immune system freak out about pollen but doesn't care about a plastic implant?
First, we've got to clear up a little bit of terminology that's super important. An antigen is anything your immune system can recognize, but an immunogen is something that actually provokes a full-blown response. Think of it this way. An antigen is a face in a crowd that your immune system sees, but an immunogen is the face that makes you stop, do a double take, and realize something is up.
So what makes a good immunogen? What really sets off the alarm bells? Well, a few things are key. First, size matters. Big, bulky molecules are much more likely to get noticed. Second, how foreign is it? A protein from a totally different species, like a bacteria, is going to trigger a much bigger response than one from a closely related mammal. And finally, complexity. Complicated proteins with lots of different shapes and folds are way better at sounding the alarm than simple, boring, repetitive molecules.
Now, to really understand these rules, it's super helpful to look at what happens when they get bent, or just completely broken. So let's explore two fascinating exceptions that show just how clever and sometimes dangerous this whole system can be. First up, we've got these things called haptens. These are tiny little molecules that are too small and too simple to be immunogenic all by themselves. Your immune system can see them, sure, but they can't start the fight on their own. It's like an alarm signal that's just too quiet to hear. And right here, you can see exactly why this is so important. By itself, the hapten is basically invisible, but if that same small molecule hitches a ride on one of our own larger proteins, a carrier, well, the whole game changes. Now the combined package is big enough and complex enough to be grabbed by an APC, presented to a T cell, and trigger that whole immune cascade. And this right here is the mechanism behind a lot of drug allergies, like the ones some people have to penicillin. Our second exception is even more dramatic. Superantigens. These are nasty molecules that some bacteria make, and they completely short-circuit the entire system. Instead of relying on that careful, specific, one-in-a-million fit, they act like a master key, just forcing a connection between APCs and T cells that don't even match. This can activate a massive portion of our T cells all at once, sometimes more than 10%. The result is a dangerous, uncontrolled cytokine storm, which can lead to severe systemic inflammation. So we've seen how our immune response is built on this incredible foundation of specificity, of selecting just the right cell out of millions. But cases like superantigens show us that backdoors exist. And that leaves us with a final thought. What other shortcuts are out there in this system, and could we potentially harness them, not just as dangers to avoid, but maybe as new keys to unlock future therapies?